Thank you. Good morning, everyone. This is joint work with my advisor, Daskalakis, and Nick Gravin. We're going to be talking about Markov chains. So Markov chains and Markov models in general have been successful at modeling sequential data or time series data across a wide range of disciplines. So in this example, we have a Markov chain, which is trying to capture like how the stock market is changing. A natural question one might be interested in asking is can we, with access to data, test if a particular model that we proposed is accurate? And answering this question is made complex by the fact that in many of these scenarios, we have no control over the Markov process, in the sense that we cannot ask for restarts of the chain. We only get to see one long trajectory, and we have to make a decision based on just these observations. And so in general, when we have like a sequence of observations x1 through xm, property testing and like other statistical questions have been studied a lot when this data are coming from an independent or moreover i.i.d. processes. And both finite sample analysis and asymptotic analysis are well understood in this setting. However, when we impose a Markovian dependent structure on this data, much less is known about how can we do inference tasks or property testing tasks, and our work explores this direction. It fits in the broader theme of property testing questions relating to high-dimensional distributions, where you get access to only a single sample. So in this case, the trajectory x1 through xm we observe is like an m-dimensional distribution, you can think of it, and because there are no restarts allowed, it's like you only have a single sample. And to put some more notation, we're going to focus in our work on discrete state Markov chains. We're going to assume they're supported over states 1 through n. I'll use capital letter P to represent both the chain and its transition matrix, and P naught will be the starting state distribution of the chain associated with P. And this is the type of the question we want to answer in our work. Given a description of a chain Q and access to a trajectory from another chain P, how long a trajectory do we need to observe before we're able to tell whether P is Q or far from Q? So there exists some literature which explores property testing and estimation questions in the Markovian setting. However, this has focused mainly on testing either the mixing properties of the chain or what are the properties of the stationary distribution. So in our work, we're more interested in like how we got there. That is like what we call the mechanics of the chain rather than the end result. So this problem is much richer, and in particular, two chains with the same stationary distribution can have very different trajectories. Now, one thing I've left out in this question is like, what is this D function? So what do I mean by distance between two chains? Let's look at it more carefully. So we want to come up with a quantitative notion of difference between two chains, which would help us answer the questions of the following form. If I give you a trajectory x1 through xm, and I tell you it's coming either from chain P or chain Q, how well can you distinguish which of the two cases it is? And we would like a distance notion to be able to precisely capture this ability to distinguish between these two things. And so we naturally have to look at what are called word distributions associated with the Markov chains. So they are probability distributions over L length sequences or alphabet of the chain. And to every string of length L, they assign a probability which can be written in a closed form. So the question is, can we characterize the statistical distance between the word distributions of chains P and Q? And it turns out that if you're willing to work with the Hellinger square distance instead of the total variation, there does indeed exist a nice closed form for this distance. It was observed by Kazakos in the late 70s that 1 minus the Hellinger square between the word distributions has this nice form. So it's like a vector matrix product here, and so this vector is a function of the starting state distributions of the chains, which let's ignore that for the moment. The key quantity here is this matrix, which we're taking the transition matrices of the two chains, doing an element-wise product, and then performing an element-wise square root on it. And this is the matrix which is being raised to the power L, which is the length of the word. So this matrix is roughly capturing how fast the two word distributions are going to diverge, if at all they do diverge. So starting from this expression, we want to boil down to a sort of a single parameter notion. And so notion of difference between two chains. And so we propose in our work as a distance between two Markov chains, 1 minus the maximum eigenvalue of this matrix, which we call PQ square root. This roughly quantifies how fast the word distributions are going to diverge. So let's look at an example to get a bit more intuition of how this notion of distance might behave. So here we have 3 Markov chains. Each is supported over, has 2 connected components. M1 and M2 are identical in the bottom connected component, and M2 and M3 are identical in the top connected component. And our notion of difference will say that the distance between M1 and M2, which might somewhat surprisingly, is actually 0. The way to interpret this is that if an adversary is choosing a worst case starting state distribution, that is, he chooses a distribution supported solely on this component, then no matter how long a word you observe, you'll never be able to tell M1 apart from M2. Similarly, the case for M2 and M3. So another thing which this example shows is that the distance notion is not a metric. It violates the triangle inequality. Okay. Cool. So with this distance notion in mind, we completely formalize the problem we look at in this work, which we call identity testing for Markov chains. And as a first foray in this direction, we focus on symmetric Markov chains. A summary of results, we show both upper bounds and lower bounds for the identity testing problem. So first, we've given an algorithm which takes a trajectory of length, the cover time of the model Markov chain Q plus n over epsilon, and outputs an answer whether P is equal to Q or far from Q. So the cover time is defined as roughly the expected time you would need before you hit all the states in your Markov chain. And for many reasonable classes of chains, it's actually pretty small. For instance, if you think of a Markov chain supported over the grid graph or over expander graphs, it turns out that it's nearly linear. To complement our upper bound, we have a lower bound which shows that the second term in the upper bound, which is n over epsilon, is necessary. So you need to observe a trajectory of length at least n over epsilon to answer this problem. Cool. So a brief idea of how we show our upper bound. The key lemma is with this one, which says that if your trajectory is longer than the cover time of the chain from where we're getting samples, then we can guarantee with good probability that we actually visit every state some minimum number of times, which is like m over n roughly, where n is the number of states. And what this allows us to do is to take long trajectories of the chains and use them to simulate i.i.d. samples from this distribution capital P over n. So what is this distribution? We take the transition matrix P of the chain, and we multiply every element with 1 over n. So now, and if we flatten it out, we can view it as a distribution over n square elements instead of n elements. And once we are able to simulate these i.i.d. samples using black box results from property testing in the i.i.d. setting, we obtain our upper bound. And our lower bound, the main technical challenge here is adapting a well-known construction of Paninsky for testing if a distribution is uniform or not to the Markov chain setting. I don't have time to go into the details of the lower bound, but if you have more questions, come find me at the poster session. Thank you.
Okay, any questions?
So people have studied questions of the form like they were more interested in whether you're reaching the right stationary distribution or whether your chain is fast mixing or not. And people have also analyzed how does a test devised for the i.i.d. setting perform if the data is Markovian. But they haven't explicitly, it was somewhat surprising for us. We didn't find anything which studies which does a principled analysis of how you can do property testing in the Markovian setting.
Okay. Yeah, one more.
So do you really need discovering time, or you can do something like mixing?
So yeah, we can first, I guess we can improve the covering time to hitting time times log hitting time. So covering time is an upper bound on that. And we actually believe for our notion of distance that we proposed, because it was carefully constructed, we don't need any covering time or mixing time. We believe that the lower bound is the right answer, but we haven't been able to show it yet.
Okay, let's thank the speaker again.